Welcome back. This is 6.2.2. In this chapter, we are going to study the DTFT of both periodic and aperiodic signal. Please remember that DTFT is typically used to analyze aperiodic signal, but it can also be used to analyze periodic signal. We'll show you how in this section. The trick of getting the DTFT of a periodic signal is this. What we do is that we first compute the DTFS coefficients of the periodic signal. That's trivial. We just apply this equation, and in this equation we can take one single period and apply these equations to find Ck for k equals to 0 to n minus 1. Now once we have found Ck, we have just simply found the DTFS representation of this periodic signal. How can then we take this DTFS representation and use that to represent it as DTFT? What we simply do is to apply this process. We take the Ck and put it here, and we multiply the Ck values by 2 pi, and what we do is that we put a delta functions at every omega equals to 2 pi n over n times k for the corresponding Ck, and we do it for all the k's from 0 to n minus 1. What we have by doing this process is simply to take the representation of Ck and express it in terms of the DTFT, where now omega is continuous. If you say that if omega is continuous, how can we represent distinct values of Ck? Is simply to use the delta functions. You also be wondering, why don't we just apply this DTFT analysis equation and simply plug it in and find x of omega? And the reason is this: if you try to plug in the periodic signal which exists from minus infinity to infinity and into this equation, you are trying to add infinite values of xn of infinite support, and these values do not converge. So x omega cannot be simply found this way. Instead, for periodic signal, this is the only way we can use the DTFS, and then by using delta functions find the expression of x omega. In the next slide, we'll convince you why this representation is the correct representation for the DTFT.